Longest increasing subsequence. How do you find order in chaos? Longest increasing subsequence is a Pattern Mastery 100 and interview favorite. Regularly asked at Amazon, Microsoft, and Google, because it tests whether you can spot patterns and optimize solutions. Most candidates start with brute force and get stuck. But if you learn the right DP or binary search trick here, you'll be ready for any sequence challenge interviewers throw your way. Let's break it down. Given an array of integers, find the length of the longest subsequence where each number is strictly greater than the one before it. Remember, a subsequence can skip elements, but order matters. Let's assess the options. The brute force approach tries all possible subsequences. Exponential time. That's not scalable. The classic DP approach is O(n)(. For each element, look at all previous elements to find the longest subsequence ending there. But with patience, you can improve to O(n) log n. Using binary search, maintaining a tails array where each value represents the smallest possible tail of an increasing subsequence of that length. Let's start with a DP approach for clarity. Create a DP array of the same length as nums, filled with ones. Each element is an LIS of at least 1. For each I from 1 to n1. For each j from 0 to i1. If nums I greater than nums j, set dpi equals max dpi, dpj, plus 1. The answer is max dp. Let's try to implement it using solution 1. Time complexity is O(n)². Space complexity is O(n). This approach uses dynamic programming. The main idea is that for every position in the array, we calculate the length of the longest increasing subsequence that ends right there. Then we compare earlier numbers to see if we can extend an increasing sequence into the current number. We store these best lengths in a DP array so we do not have to recompute them repeatedly. And we keep track of the best result we have seen overall. Here we define the function and immediately handle the simplest case. If the array is empty, there cannot be any increasing subsequence. So we return 0 right away. This keeps everything clean. And it avoids edge case issues later. Now we create our DP array. Think of DP at index I as the best increasing streak that ends exactly at index I. Every single number can at least be a subsequence of length 1 by itself. So we start everything at 1. We also set up max len to remember the best answer we have found so far. This is the heart of the strategy. We walk through each number as the current endpoint using I. Then for that I, we look at every earlier position j. The goal is to ask if the sequence ending at j can be extended by the number at I. Here is the rule for growing a subsequence. First, the number at j must be smaller than the number at I. That is what keeps it increasing. Second, we only update dp at I if extending the sequence from j actually gives a better result than what dp at I currently has. If it does, we store that improved length in dp at I. After we finish checking all earlier values for this I, we now know the best increasing subsequence that ends at I. So we compare dp at I against max len. And if it is bigger, we update max len. This ensures we always know the best answer across the entire array. Finally, we return max len. Max len represents the length of the longest increasing subsequence found anywhere in the array. And that's how this algorithm works. It first sets up a DP array where each position starts at 1 in a max tracker. Then it compares each number with all previous numbers to extend increasing sequences and keep the best length. Efficient, simple, and elegant. Test case check, LIS using dynamic programming. Let's test our function using this input. 10, 9, 2, 5, 3, 7, 101, 18. These numbers represent a sequence of values, and our goal is to find the length of the longest strictly increasing subsequence hidden inside the array. Here's why the solution works. Our DP array, dpi, represents the length of the longest increasing subsequence ending at index I. For each number, we look back at all previous numbers. If a previous number is smaller, and extending its subsequence makes ours longer, we update our dpi value. This way, we gradually build up all possible increasing subsequences. In this specific example, one valid longest increasing subsequence is 23718, which has a length of 4. The DP computation captures this perfectly as it iterates. And that's exactly what our program outputs, 4. The result matches the expected value, confirming that our DP logic is working correctly. Wrap up. So, our implementation is correct. The algorithm successfully computes the longest increasing subsequence using dynamic programming, efficient and accurate. Let's try to implement it using solution 2. Time complexity is O(n) log n. Space complexity is O(n). This approach uses a clever idea often called the tails method plus binary search. Instead of building the actual longest subsequence directly, we maintain an array that stores the smallest possible ending value for increasing subsequences of different lengths. Each new number either extends the list, meaning we found a longer increasing subsequence, or it replaces an existing tail with a smaller ending value, which makes it easier to build longer sequences later. Binary search helps us find the correct position fast. And that is what keeps the solution efficient. First, we set up our function and create subseq. Think of subseq as a tracking list. At each index, it stores the smallest possible ending number for an increasing subsequence of that length. Smaller endings are better because they give us more room to grow later. Now we walk through each number one by one. For every new number x, we decide where it fits into our subseq tracker. Does it help us create a longer subsequence? Or does it improve an existing one by giving it a smaller ending value? Here we prepare for binary search. Our goal is to find the earliest spot where x could go without breaking the increasing order. In other words, we are looking for the first position where the current value is not smaller than x. That position is exactly where x should replace something, or where it should be appended. This loop is the fast search step. We keep shrinking our search window until we land on the best index for x. If the middle value is still smaller than x, we know x belongs further right. Otherwise, we move left. By the end, left becomes the correct insertion or replacement position. Now we apply the decision. If x lands exactly at the end, that means x is bigger than all current tails. So we have extended our best length so far. And we append x. Otherwise, we replace subseq at that index with x. That replacement does not change the length yet, but it improves our chances to build longer sequences later, because we are keeping the smallest tail possible. At the end, the length of subseq tells us the length of the longest increasing subsequence. Even though subseq may not literally be the longest increasing subsequence itself, its size accurately represents the best possible increasing length we can achieve. And that's how this algorithm works. It first sets up a subseq array to track the smallest possible tails for subsequences, then it uses binary search for each number to either extend subseq or replace a tail to keep future growth easier. Efficient, simple, and elegant. Test case check. Optimal LIS, binary search plus patience sorting. Let's test our function using this input. 0, 1, 0, 3, 2, 3. These numbers represent a sequence where we want to find the longest strictly increasing subsequence hidden inside the array. Here's why the solution works. We maintain a subseq array that stores the smallest possible tail for an increasing subsequence of each length. Using bisect_left, we either append a new number when it extends the sequence, or replace an existing tail with a smaller one, keeping future options open. And that's exactly what our program outputs. 4. This confirms that the optimal patience sorting method calculates the LIS correctly for this test case. So, our implementation is correct. The algorithm successfully computes the longest increasing subsequence using binary search and a compact tail array, efficient, accurate, and reliable. Longest increasing subsequence. Let's do a recap. We started by understanding the goal. Find the length of the longest subsequence where each number is greater than the previous one. The key detail, it's a subsequence, not a subarray, meaning we can skip elements, but must keep the order intact. Assess recap. We compared different approaches. The brute force method checks all combinations but quickly becomes impractical. The dynamic programming approach, with O(n)² complexity, gave us a structured and efficient way to build solutions step by step. And we discussed how an advanced binary search technique can push that to O(n) log n, for even larger inputs. Structure recap. Our DP plan was simple. For each element, look back at all previous ones and track the length of the longest subsequence that could end there. Each number starts as a sequence of length 1. And we update those lengths as we find valid increases. Implement recap. We implemented this logic cleanly in code, ensuring each element's LIS length was computed correctly and ran the function on LeetCode without any syntax or logic errors. Check recap. After running the test case, 0, 1, 0, 3, 2, 3, we confirmed our output was 4, matching the expected result. Our approach passed all test cases successfully. Closing insight. The big takeaway? Pattern problems like this reward structure over guessing. Once you understand how to build solutions incrementally, or even optimize them with binary search, you'll start to see order emerge from the chaos every time.